Hey everyone, it's Bradley Bush again with an algebra video. But today we're talking about systems of nonlinear equations in two variables. Because we're in two variables, that means we're in two-dimensional space. And here's our to-do list. The first thing we'll talk about is a quick overview, hopefully to kind of bring us up to speed to nonlinear equations. So we'll talk about systems of linear equations in two variables and three variables. And then we'll talk about an example of a line in a circle in a system, and we will solve it, meaning we'll find out where they touch, if at all. So what exactly is a system of nonlinear equations in two variables? Because it sounds kind of complicated. Really, it's just a lot of math speak. Two variables just means we have an x and a y, meaning we have two variables in our equations. Nothing big there. The fact that they are nonlinear, that just means that we're not restricted to lines in our systems. So if you're doing nonlinear systems of equations, you probably have already done linear systems of equations. So you've been dealing with lines or planes. But now we're not restricted to lines, things that are straight. So we can have parabolas, we can have an ellipse, a circle. We've got lots of options. So that's the nonlinear part. The system, word system, just means we have more than one equation. So here we're going to have two equations. So we have two variables, two equations. No biggie. So I don't think I would even say that it was complicated even if you offered me a large taco. Just saying. So here's your review for linear equations in two variables. You can see we have two equations here. They represent lines. This specific equation, or system, touches at one spot, the xy coordinate, -2, 5. So that's the solution to that system. Our options, remember, for linear equations in two variables, we had one solution where they touch just once, as in the example we showed up top. No solution because the lines are parallel and never touch, or infinite solutions because the lines are actually the same line and any point on one line is also a point on the other. So every point touches that's on either of the lines. So those are the options: no solution, one solution, or infinite solutions. If we moved into three variables, here we have a system, meaning a group of equations, and we've got three variables, x, y, and z, and we have three equations also. This specific system touches at one point, and it touches at -1, 2, and -2 for your x, y, and z coordinate. So since we're in three-dimensional space and we have three variables, you have to think of these as planes. So you've got three planes in three space, and you could have one solution as far as your option category, where you could just have all three planes touching at one specific spot, only one x, y, z coordinate. Or you could have no solution, where you can see these three planes here are parallel in the top picture. In the second picture here, you can see that there's some spots where the red and the green touch, or the purple and the green, but never all three of them at the same time. Or you could be in the situation where you have infinite number of solutions. So every point on this line right here that's a vertical line is a solution to the system, because these planes touch in this vertical line. So there are an infinite number of them. So we again have the same categories for numbers of solutions: one solution, no solution, or infinite solutions. That brings us to nonlinear equations. Nonlinear equations don't quite have these same categories. They do have the no solution option. And I guess if you had two systems, or you had a system that had two objects that were identical, you could have infinite solutions, but we don't necessarily have the only one solution category. Like, for example, this one here. The first equation is a line. You can see it over here in the red line there. The second equation is a circle with center 2, 3, and a radius of 2. So where do these two things touch, the circle and the line? Well, you can see they touch in two spots, 0, -3, and 2, -1. So already we've kind of broken our one solution category. So here, when we're talking about nonlinear equations, it's a good thing to try to graph them or try to at least visualize what you're looking at, because that can help you. You might have more solutions or more touching points than you might think, and it's good to see what we have. Here, we're going to actually solve the system algebraically, so we can look at it and say, hey, we know we're looking for two solutions. And a note on the nonlinear. You can tell you have a nonlinear system when you start to see things like a 2 in your exponent, because linear systems just have an implied 1 on all of the variables. So you really don't see an exponent. But in nonlinear systems, you will see exponents. You'll see 2s, you'll see 3s. So keep that in mind. Well, let's actually solve this system algebraically. So we have our system. We have equation 1. We have equation 2. And if we're looking at this, the solution techniques are going to be kind of similar to linear systems in 2 and 3 variables. We'll try to use substitution and addition. So those are our main methods of solving for these. So if we took equation number 1 and we solve for x, and then we substituted it into equation number 2, then we just have y's left and we can solve for y. So let's try that. Here we have equation 2. Instead of having an x, we need to plug in what we found when we solved for x in equation 1. What do we have? So if you take x and you isolate it, we will add y to both sides, and we get x equals 3 plus y. Not really sure what that squiggly thing was. So we have x equals 3 plus y. We can plug that in down here, 3 plus y, because that was where x was, right? Now we can start to do some algebra. Now we just have y's left, so we can just solve for y. We can get rid of these parentheses here and just have 3 plus y minus 2, which gives us y plus 1. Awesome. Now we have y plus 1 squared plus y plus 3 squared equals 4. Now we can solve for y. So this is going to end up being a quadratic that we probably will factor. So what is y plus 1 squared? Well, if we factor that out, if we FOIL that, which is the opposite of factoring, we get y squared plus 2y plus 1. And if we multiply out y plus 3 quantity squared, we get y squared plus 6y plus 9, and then we have the 4 still on the right side. So just to make sure we know where these things are coming from, the y squared plus 6y plus 9 came from the y plus 3 quantity squared when you multiply that out. And the y squared plus 2y plus 1 came from the y plus 1 quantity squared. So if we gather our like terms, we've got a y squared and a y squared. That gives us 2y squared. And we have a 2y and a 6y. That gives us 8y. And a 1 and a 9, which give us 10. Equals 4. We could divide by 2 everywhere now, because I can see all of the coefficients are divisible by 2, and that'll help us simplify. If we divide by 2 everywhere, what does that give us? That gives us y squared plus 4y plus 5 equals 2. Let's take that 2 to the other side. We get y squared plus 4y, 5 minus 2 is plus 3, equals 0. This is looking nice. Now we can factor. When we factor, let's see what we get. This will factor into y plus 3 and y plus 1. Beautiful. Now we have two things multiplied together. So this is just like saying we have an a here times a b here, and this all equals 0. So when you have two things multiplied together and the result is 0, that means either the first thing or the second thing or both are 0. So we can set both of them equal to 0 and solve. Let's try here. So y plus 3 equals 0. If we subtract 3 on both sides, we get y equals, that's kind of a terrible equal sign, -3. Beautiful. There's 1. What about the next? We haven't done b. Let's set b equal to 0. So we have y plus 1 equals 0. If we subtract 1 on both sides, then what do we get? Y equals -1. Awesome. So we have 2 of these beautiful things. That's it's a technical term, just FYI. We have 2 options for y. That's what I'm trying to say. So we need to take each of them individually and solve for the associated x. So we're going to use equation number 1, which we have written here, x minus y equals 3. So instead of having a y, let's see what we have here. First y we'll do is -3. So instead of having y here, we're going to put -3. And a negative make a positive. So we have x plus 3 equals 3. If we subtract 3 on both sides, what does that give us? x equals 0. All right. For y equals -3, we have x equals 0. How about for y equals -1? That's our second option for y. So we have -1 here. The negative and the negative give us a positive. And we have x plus 1 equals 3. Subtract 1 from both sides. And we get x equals 2. Beautiful. So what does that tell us? Well, that tells us that our solutions were, for y equals -3, we have x equals 0. And -3. Was that surprising at all? No, because look down here at the picture, 0, -3. We knew that was the solution, but we just found it algebraically. That's kind of cool. And our next solution was x equals 2 and y equals -1. Were we surprised at that? No, we weren't, because we can see over here on the right that that was another option. So our circle and our line touch at only 2 points. And those 2 points are 0, -3, and 2, -1. Hope that helps. Thanks for watching.